Hello guys, today I'm going to be talking about alcohols, ketones, aldehydes, and carboxylic acids. So starting off with identifying an alcohol, they have oxygen bonded to hydrogen as a functional group, single bonded, of course, and this is called a hydroxyl group as well. And this example is ethanol, which is what people get drunk off of. So that's pretty interesting. And next, a ketone has what's called a carbonyl group. Which is essentially an oxygen double bonded to a carbon. And this example is propanone. And okay, next, an aldehyde also has a carbonyl group, but it's essentially like a special type of ketone because one of the carbonyl carbons has to be bonded to a hydrogen. So basically it's on like the end of a chain. And this example would be called propanol with an A. Now lastly, a carboxylic acid has what's called a carboxyl group. It is essentially like a hydroxyl, and it's like a combination of a hydroxyl and a carbonyl group, because on the same carbon there is a carbonyl right here and a hydroxyl right there. And this example would be called propanoic acid. Okay, so looking at the properties of these four functional groups, they all have a carbon bonded to an oxygen. And this bond is polar because it has an electronegativity of 0.89, which is more than 0.4. So they're polar, and because of that, they have relatively high boiling point. And this is because of increased intermolecular forces between molecules. So for simplicity, let's just have an example of CO like this. Now, they experience dipole-dipole interactions, which basically means that the partially negative parts of one molecule interact with the partially positive parts of another molecule, like so. And these are especially strong when the oxygen is bonded to a hydrogen. For example, in water, they experience particularly strong dipole-dipole interactions, and they are called hydrogen bonds. So if we go in order, if from highest to lowest boiling point, we would see carboxylic acids at the start, and then alcohols, and then ketones, and lastly aldehydes. All right. So, just like taking a look at this, carboxyl groups have the highest boiling point because, firstly, they have a pretty heavy functional group, right? They have an oxygen, two oxygens, and a hydrogen, which makes up quite a bit of weight. And you have a lot of polar bonds. You have two polar bonds. Actually, three polar bonds. One here, and one between the oxygen and the hydrogen. So this creates a really strong dipole going this way, which makes for even stronger interactions. Hydrogen bonding interactions and normal dipole interactions. Now, alcohols are a little weaker because they didn't have that ketone that carboxyl groups have. So they only have this as their this generating their dipole and providing hydrogen bonds. Now, ketones are a little weaker than alcohols because have like a lower boiling point than alcohols because they do not have that hydrogen bond that alcohols and carboxylic acids did, which means that they do not have hydrogen bonding, which means that they only rely on dipole. They mainly rely on dipole-dipole interactions, which are weaker than hydrogen bonding, and that gives it a lower boiling point. And yeah, aldehydes have similar boiling points, but are slightly lower than ketones because this hydrogen cannot donate its electron density to this carbon right here, which means it can't give much of a dipole to this carbon because hydrogen is a relatively small atom with like 2 electrons, so that's why. And also, pretty much all of these can combust because they are essentially still hydrocarbons, but this time they just have oxygens as well, which can give it oxygen to fuel the combustion as well. Yeah. Also, these can be acidic in nature. Yeah. Okay. Which means they have lower pH and a lower pKa, which I will go into another video. So when naming these, we gotta consider the priorities, or like how high they list on the priority table. So basically, okay, let's take an example here. Like so. Now, there are two functional groups. So the main chain is right here, and the rest are functional groups. So we have this one right here and this one right here. This is an alcohol, this one is an alcohol, and this is a ketone. And when we look at the priority table, ketone, hold on, let me just change the color. Yeah, so alcohol falls under ketone in the priority table. And basically the highest priority functional group will be the last thing mentioned in the name, right? So it will be like a suffix, basically. Let's just do this example to make it clear. So this is a propyl group. So prop and yeah, so since ketone is the highest priority functional group, it's going to be at the end, right? It's going to be the suffix. So that's going to be prop-2-one. And since alcohol is not the highest priority, it's gonna be a prefix, right? So it's gonna look like this. I'm gonna use hydroxy instead of the suffix ol. Yeah. And that basically sums it up. So carboxylic acids have the prefix carboxy and the suffix oic acid, whereas aldehydes and ketones have the prefix oxo, and ketones have the prefix on, and aldehydes have the suffix -al, and yeah. Now going into some common reactions involving these. Oxidation reduction is a really common reaction that you will see involving these four groups. So essentially, it allows you to interchange between all of these functional groups using either an oxidizing agent or a reducing agent. So in this case, the molecules are getting oxidized, and you would use an oxidizing agent such as potassium permanganate as a catalyst. Actually, no, as an oxidizing agent. And if you wanted the reaction to go in the opposite way, so you would use a reducing agent, such as, for example, sodium borohydride, and this would turn carboxylic acids into ketones, and also turn ketones into alcohols. And a common trend with oxidizing and reducing agents is that oxidizing agents tend to have a bunch of oxygen atoms, whereas reducing agents tend to have a bunch of hydrogens in their formula. And one thing to note is that tertiary alcohols, like this, that have the hydroxyl carbon attached to three other substituents that aren't hydrogen, these cannot be oxidized, because let's just take a look at what should happen theoretically. See, you would get this thing, and this thing should not exist, because if you look at it, this carbon has 5 bonds, which should not exist. And that means tertiary alcohols cannot be oxidized to make a ketone. And adding on to that, secondary alcohols cannot be oxidized to into making a carboxylic acid, because once again, if you oxidize this again, you would see this product, which also has 5 bonds, right? That is something to recognize. Yeah, so ketones and secondary alcohols cannot make a carboxylic acid. The hydration addition reaction is a important reaction, and what it does, it essentially turns an alkene into an alcohol. So essentially, the general way it will look like is something like this. And R just stands for like anything, pretty much. And when you add water, what happens is that you get an alcohol, and the double bond goes away. So one example, I'm going to draw one example. Yeah, so we have this alkene, and the OH group will always be on the most substituted carbon, which is this one, right? So the product will look like this. Yeah. Okay. Just so you understand why that is, like why it chooses this carbon and not this carbon, I'm going to show you the mechanism of the reaction. So, okay, hold on. Let me just use 2 different colors. And water. So, when you think about it, a double bond is essentially just 2 electrons, right? And electrons like positive charge. So, and in the water, an H plus, okay, the hydrogen atom has a partially positive charge, whereas the oxygen has a partially negative charge because of the dipoles. So essentially what's going to happen is that the electrons in the double bond will reach out to the H, the hydrogen, because it's partially positive. And electrons like partially positive stuff. And also, yeah, so basically, the electrons will take this hydrogen, and the electrons will move back into the oxygen, because the oxygen is electronegative, and it kind of wants to take them anyways. And actually, there's going to be 2 possible places where the hydrogen can go, because the double bond is attached to 2 hydrogens, 2 carbons, one right here and one right here. Now, so the hydrogen could be here, or it could be here. However, when the hydrogen, there's going to be a cation that shows up in 2 possible places, depending on where the hydrogen went. Yeah. And tertiary carbocations, so like carbocations with 3 sticking to three different groups are more stable than secondary or primary cations. And as you can see, this is a tertiary, while this is a secondary cation. So that means this will not happen, or this will not form because it is less stable. They are less stable than tertiary. So this will happen. However, the full thing hasn't been completed yet, like the full reaction, because we have this cation, which is more stable than a secondary cation, but it's not really stable in general. And recall that we also have a free hydroxide ion in the solution from this first step. So now the OH group has a negative charge, and it can use its electrons and negative charge to attract itself to that positive charge, and it will essentially just make the product like so. And this habit of how the groups are mainly added to the most substitute the highest substituted carbon is called the Markovnikov rule. And yeah, now these are just some other reactions that are outside of the curriculum, the high school curriculum, but they're just interesting to look at. Just shows how like reactive alcohols, aldehydes, ketones, and carboxylic acids are, and how versatile they are in reactions and synthesizing things. So yeah, here's just a bit of nomenclature practice. You can try them now if you want, but I'm going to go over them in a couple seconds. Okay, so starting off with question one, we just have to identify the main chain, which has 4 carbon atoms, making this a butyl chain. And we also have this substituent right here, which is a carbonyl substituent. And this is a ketone rather than a aldehyde because it's not attached to an hydrogen group. The carbonyl carbon is not attached to a, this makes but-2-one, wait, butan-2-one, yeah. Looking at question 2, the main chain is also but, has 4 carbons. But this time there are 2 substituents. One looks like this, and one like this. One carbonyl and one hydroxyl. Now, recall that aldehydes are higher than alcohols on the priority table. So that means the aldehyde is going to be at the back, whereas the alcohol is going to be at the front. And it's on carbon 3, so 3 hydroxyl. Hold on. butanol with an A. Now, moving on to question 3. We have a 3-carbon chain. So this is going to be propane, and there are two, as you can see, there are 2 carboxyl groups, not to be confused with alcohols or aldehydes. So we would have dioic acid. And IUPAC nomenclature doesn't like this, how there's like 2 consonants next to each other, so IUPAC just decided to add an E here whenever like there are 2 consonants like this. Now question 4, there is another 3-carbon chain, main chain, and there are there is 1 aldehyde and 1 carboxylic acid. So instead of the aldehyde being at the back, this time the aldehyde is going to be at the front. So we're going to have 3-oxo. Yeah, it's going to be 3 because the carboxyl carbon is going to be number 1. So it's going to be 3-oxo propanoic acid. All right. Now let's just look at some drawing practice. Let's draw the main chain. So first, starting off with 1, the main chain is just the carbon. And we have diol. Actually, I think this would be dione. Yeah, but anyways, we have 2 ketones. So it looks like this, which is a bit of a trick question because it's actually carbon dioxide. But yeah. And moving on to question 2. First, we'll just draw the main chain. So 1, 2, 3, 4 carbons. Now let's draw this. Oxalic acid means that there is going to be a carboxyl group, so OH and a double bonded O. And 3-hydroxy means there's going to be an OH on carbon number 3. And that's what it will look like. Now question 3, penta is the main chain, so 1, 2, 3, 4, 5 carbons. And this time we have methyl. So 1, 2, 3. And this is a triol, so there's going to be 1 OH right here. Hold on, let me use a different color. So there's going to be 1 OH on number 1 and 4, 4, so 2 hydroxyl groups on carbon number 4. And yeah, that's it. Goodbye.